Hello, welcome to our first lesson back from the break. I have a very special guest with us at the moment. This is Cookie the cat. She likes to be a pest when I start recording my videos. Just thought I'd have her say hi. All right. So we're talking about higher derivatives and concavity. So what's a higher derivative? I think higher order is the full term, but I only have so many characters to enter in these little titles here on the screen. Well, when we've been talking about the derivative, this is technically called the first derivative. So we call the derivative, which is f prime, excuse me. So we call this the first derivative of the function f. But you can have other types as well. For now, we'll focus on the second derivative. And this will be our primary focus today. So the second derivative of the function f, which we call f double prime. So the number of primes here indicates the order of the derivative. So what is this thing? Well, it's the derivative of f prime, the derivative of the derivative. So f prime is the derivative of f, and we call it the first derivative. The second derivative of f is the derivative of f. So these higher order derivatives, that means you just take the derivative of the previous derivative. So for example, let's say we have 7x cubed minus 12, x squared plus 5x plus 20. The first derivative, we're using power rule, like so. Then the second derivative is just the derivative of f prime here. So we take the derivative again, gets us 42x minus 24. A practical application of this is acceleration. So we'll do a mini physics problem here. So this is when your original function, f, is position. Suppose the position of a particle at time t is s of t, which is x times e to the x. That might not be a very realistic position function, but it works for this problem. Okay, so if the position is given by that s of t, then the particle's velocity, which is essentially speed, it's the rate of change of position. The only difference is that velocity can be a negative value, which means you're going backwards. But think essentially speed. So the particle's velocity, the rate of change, is s prime of t, the derivative. So we take the derivative of s of t. Notice that that's a product of two functions. Oh, yeah, sorry, these are supposed to be t's. My mistake. Gotta correct my notes on that one. So we do product rule. This is a product of two functions of t. So I'm taking the first times the derivative of the second. Well, derivative of e to the t is itself. Plus, now I take the derivative of t times e to the t. And to simplify, I can factor out an e to the t. Okay, so that was product rule. Now this new thing, the particle's acceleration is the second derivative. Acceleration is the rate of change of velocity. So how fast is your speed changing, essentially? Let's put that in writing a little bit. The rate of change of velocity this is s double prime of t, the derivative of s prime. So this is d dt, the derivative of s prime of t. Okay, now the cat's off my lap. There we can see it. So this is also a product rule. I have a product of two functions of t. So first times the derivative of the second, derivative of t plus 1 is just 1, plus derivative of the first, still just e to the t, times t plus 1. So notice I have an e to the t in both terms again, so I factor that out. And that can be simplified as a times t plus 2. So acceleration is the rate of change of the rate of change of position. So how fast is the speed changing? Now, you might be thinking, well, is there any limit to how many derivatives I can take? And the answer is no. So we can take a third derivative. And that actually has a real application here. So the third derivative, which we call s triple prime of t, right? 3 primes, the third derivative. So for this particular type of problem, where your original function s is position, we call the third derivative jerk. And that's for a good reason, not because it's mean, but it's because when you're driving in a car, it's when your acceleration changes or there's some non-zero value to the third derivative, that is when you actually feel the pull of the car. Otherwise, like if you're traveling at a steady velocity or even a steady acceleration, where that speedometer is just going up at a steady rate, or I guess this way for you, I think you're thinking of reflections here. um, so if your speedometer is going up at a steady rate, that means your acceleration is constant. and then it feels kind of like you're sitting on a park bench unless you're on a bumpy road. But it's when that acceleration changes, that's when you feel this pull, when the third derivative is not zero. So we call that jerk. So that's a real thing that we experience. And we can take even higher order derivatives yet, but eventually we stop this convention of writing all these additional primes. So I'll just say for fourth derivatives, and higher, we change our notation. And I'll switch back to F here. You put this as a superscript, and in parentheses, the number of primes that you would have, or the order of derivative. So the fourth derivative, you write f4 of x instead of 4 prime symbols. For the fifth derivative, f5 of x, and etc. So our main focus for today is on the second derivative. It will have some useful things to tell us. So the feature of a function that relates to the second derivative, it's called concavity. The first derivative of a function told us when the function is increasing or decreasing, and the second derivative will tell us where the function is what's called concave up or concave down, and I'll explain what these mean. So f prime tells us when f is increasing or decreasing. That's when the derivative is positive or negative. And then f double prime, the second derivative, well, by the same logic, it tells us when f prime is increasing or decreasing. That's because f double prime is the derivative of f prime. So when f double prime is positive, that means the derivative f prime is increasing. So what does that look like with respect to f, the original function? So let's focus on that positive part. So if the second derivative is positive on an open interval, it means f prime is increasing on that interval. And this means the same thing as f is concave up. So what that looks like, just a rough demonstration, it means that on that open interval, your function will have this shape, excuse me, that kind of looks like x squared, where it's opening upward. So this is concave up. So relating that to the derivative here, it means that the slopes of tangent lines are increasing as we move along. So for example, here's the tangent line at this point. It's negative. If I go farther along, like over here to the right, well, this is a greater slope because it's actually positive. This one's negative and will be more steeply in the positive direction over here. So as you move along, the slopes of the tangent lines are increasing. That means the derivative is increasing. So this is concave up. The slopes of tangent lines are increasing. On the flip side, if the second derivative is negative, that means the derivative is decreasing, which will mean that f is concave down on that interval. And that'll look something like this, the opposite of concave up. So in this case, as we move along, the slopes of tangent lines are going down. Like over here on the left, I've got a nice positive slope. Well, at this point, it flattens to 0, roughly. And as we keep moving along, we're now having negative slopes. So the slopes of the tangent lines are decreasing, which means the derivative f prime is decreasing. So I'm going to do a graph problem. I want us to get familiar with what it looks like to see what's concave up versus what's concave down. So in this problem, we're not even going to take derivatives, but just look at a graph. So here's a graph of y equals f of x, making it something like this. We hit the origin and go back up. So it is possible just by looking at a graph to tell where it's concave up or concave down. On this left half here, the graph is concave down because it looks kind of like the graph of the upside down parabola, like negative x squared. This thing is opening downward. And if you're really not sure, you could just draw the tangent lines and you'll see that the slope is decreasing. Right, it's very sharply positive down here, but then it flattens up here and then becomes negative on this side. So on this left half of the graph, we're concave down. So f is concave down on the interval from negative infinity to 0. And we just stick with open intervals. So I stopped at 0 because notice that here on the right side, that looks a lot more like the shape of the standard parabola x squared, right? Something that's opening upward. So that's what concave up looks like. So from 0 to infinity. That means then that there's some sort of turning point here in the middle. And that has a special name. It's called the inflection point. And there could be more than one on a graph. In this case, there's only one. But an inflection point is a point where the concavity changes. All right, let's zoom out a little bit. So in this example, the origin is the inflection point because on the left side of it, my graph is concave down, but on the right side of it, my graph is concave up. So because of that switch, that's an inflection point. Okay. So how do you find one? When in this example, we were able to visually tell that's where this shift happens. But say you don't have a graph, then it boils down to the behavior of the second derivative. So this can only happen when the second derivative is 0 or undefined. So notice this is kind of like a critical point, right, with the first derivative. So critical points were candidates for local maximums or local minimums. So this is the equivalent with the second derivative, except we're not focused on endpoints this time. But if the second derivative is 0 or undefined, then that's a candidate for an inflection point. But you do need to check. It's not guaranteed to be an inflection point. An inflection point is where the concavity changes. So we still have to check that. But this will give you your candidates. So let's do an example. Without a graph, we're going to find the open intervals on which this polynomial x cubed minus 3x squared minus 9x plus 15 is concave up or concave down. We're going to find all those intervals. And we're going to find any inflection points, if there are any in the first place. All right, so the question of concavity and inflection points, it all boils down to the second derivative. So we'll need that first. Well, first we have to take the first derivative and then take the derivative of that. You'll notice I'm doing a lot of polynomials today. Your homework does have other things, but you can handle them, and I need to save time. So we have a lot to talk about. Okay, so for f double prime, just took the derivative of f prime. And we can factor out a 6. Makes this a little easier to analyze. This is a polynomial. It's always defined. So if we're going to find inflection points, it's going to be where this is 0. So maybe I would say that there's a potential inflection point at x equals 1. We need to check. So we need to make sure that the concavity really changes around that point. And the way we do this is we draw a number line like we were doing before with the first derivative. And here's 1. It's the point I'm checking. And we're going to test points around it and see, is the second derivative positive or negative in these regions. All you need to do is test 1 point, because you will experience uniform behavior on each side of this 1. So let's plug in 0 into the second derivative. That will determine if we're concave up or concave down over here. So here, that's the second derivative. So 6 times 0 minus 1 is negative 6. The most important thing is that that's negative. So this means that this entire interval will be concave down in our function f. Now we only have an inflection point here if it changes, if we're positive on the other side. And that's something we have to check to make certain of. So I'll plug in 2. And indeed, this becomes positive. It's positive 6. So this entire interval, the second derivative is positive, which means we're concave up. So now we can clearly see, okay, there's a shift in concavity around that point. So we have an inflection point there. We can wrap this all up. Let's say that first. Talk about the inflection point. So since the concavity changes, around when x is 1, these are x values here on the axis. So we know that it changes, therefore we have an inflection point. We did need to check that to make sure, because it could have been a scenario where it's negative and then negative again over here. Now that's not what happened, but it could happen in theory. So you need to check. All right, so we found our inflection point. And we know that since the second derivative is negative over here, that means my function f is concave down. So from negative infinity to 1, f is concave down. And we're concave up on the right side from 1 to infinity, because we know that the second derivative is positive over there. And we have an inflection point. I'll just give the full point. It's at the x value 1 and the y value is 4. And I got that from plugging it in to the original function, plugging in 1. And I'm kind of skipping that step. But that's how you get the full point. So when you encounter a problem in Pearson, just check to see if they're asking for an entire ordered pair like this, or if they're just asking for the x value. That'll determine how you enter your answer. So concavity and inflection points, it all boils down to that second derivative. Now, a really nice feature of second derivatives is that they provide another test for us to find relative extrema, that is, a local maximum or a local minimum. This is called the second derivative test. We learned about the first derivative test last time. That involved the first derivative. So this is another test which uses the second derivative towards the same purpose. We're trying to classify critical points. So you have a critical point on your function, and the second derivative test will tell you, is this a local maximum or a local minimum? Potentially. You'll see that there are some caveats here. So first thing is that it's critical points of a specific type, the most common type, where the derivative is 0. Remember that you also have a critical point where the derivative is undefined, or at an endpoint if your domain is suddenly cut off with a closed interval. So the downside of this test is that it does not apply to those cases. It only applies to this type of critical point where the derivative is 0. Now, this is the most common thing that you encounter, but this test is limited, so that's the downside. We'll see that there's another limitation as well. So if we have a critical point or a critical number c, that's just the x value, of the type where the derivative is 0, and well, you want the second derivative to exist in the first place. There we go. Then you can use that second derivative to classify this as a local maximum or a local minimum. If the second derivative is negative at that point, then this means that you're dealing with a local max. So the reason is, if the second derivative is negative, that means we're concave down. And this little top of the hill, that's where the first derivative is 0, because the tangent line is horizontal, so 0 slope. And when you think about it that way, we're concave down, then this flat point is on a hilltop, so it's a local maximum when x is c. So I always found that a little counterintuitive when I was first learning this. If the second derivative is negative, that means you're at a high point. But that's why it works, because you're concave down. If the second derivative is positive, that means we're concave up on this interval. So it looks more like this. And that means that our flat point is at a little valley. It's a local minimum. It's lower than all the points in its little neighborhood. However, you still have this other possibility of the second derivative being 0 at that point. And unfortunately, this means that the test is inconclusive. So if this happens, if the second derivative is 0 at your critical point, then you have to do something else. You must use the first derivative test. That'll do it for you. So this one is inconclusive. Let's zoom out a bit. There, that's the second derivative test. So my assessment of this, I generally prefer the second derivative test over the first one. Most of the time it works out more nicely, but the downside is that this does not work in every situation. It only applies for this specific type of critical point, and if the second derivative is 0 there, then that also doesn't tell you anything. So the second derivative test, it's a little bit more limited in scope, but it still works in most situations. I would say usually when it does work, it's the better option than first derivative test. That's my own preference. But the good thing about first derivative test is that it always works. I just find it to be a little more tedious most of the time. Let's do an example. I'm going to use the second derivative test in particular. When it comes to exam time, you'll want to be able to do both. Just understand both tests and be able to do each one. They both serve the same purpose of classifying critical points, but they just use different means. First derivative test uses the first derivative, second derivative test uses the second derivative, f double prime. Let me finish my sentence here. Use the second derivative test to find relative extrema. Again, that's just talking about local maximum, local minimum. This one is also a polynomial, but it's at least written in an unusual form. So at least that's something different we're doing. Now you could, in theory, multiply all this out to get it in a standard form, but we're not going to do that. We're going to get some practice in using product rule and chain rule. If we're doing the second derivative test, then we need to find the second derivative. And in order to do that, we'll need the first derivative first. Notice I have a product of two functions of x. So we need to use product rule. I'm going to leave the first one alone, then take the derivative of x plus 8 squared, then plus the reverse, take the derivative of 3x, and then I leave the other one alone. Notice that this here is chain rule because I have a function x plus 8 inside of a squaring function. So that's composition. Remember, with chain rule, you do the derivative of the outside portion first. So I bring the 2 down, leave the inside alone, and subtract 1 from the power. And then I multiply by the derivative of that inside x plus 8. Its derivative is just 1. And then we have this other part here. And it would be convenient for us to simplify a bit before we take the next derivative. So we've got a 3x times 2. Let's look for things that we can factor out potentially. I have an x plus 8 here, and there's one of them here as well, plus an additional. And I have a 3 in each term as well. So I'm going to factor out a 3 and a single x plus 8. And then what is left over, I just have a 2 left in this term. And there was another x plus 8 here. Oh, I made a mistake. There was this x here as well that I didn't factor out. Sorry, so this was a 2x. This 2 and this x here. There we go, that's right. Then I can simplify a little more by adding the 2x and x together. So that's a pretty good simplified form. I could FOIL this, multiply it out, but I won't. Let's move on to the second derivative. We'll need that to do the second derivative test. Well, let's move this 3 out. It's just a constant, so we can kind of forget about it for a moment and just deal with the parts involving x. And so this will be a product rule on that part. Here's x plus 8 times the derivative of 3x plus 8. It's just 3. Plus derivative of x plus 8 is 1 times this 3x plus 8. So that was product rule I just did. And now we can simplify that a little more. So we still have that outside 3. And I can distribute this 3 here. It's a 3x plus 24 plus this 3x plus 8 over here. And combine like terms. Have a 3x plus 3x, 6x, plus 24 plus 8, that is 32. And I can factor out a 2 from each term. It would give me a 3x plus 16. So here's the most simplified version. So let's ask, what is the goal of the problem? The goal is mainly to classify relative extrema, that is, find the points which are local maximums or local minimums. That's the main purpose. And we're going to use the second derivative test to that end. But I actually need to focus on the first derivative first, because we need to test critical points. You find critical points from the first derivative. So where is the first derivative 0? Or undefined, or an endpoint? Well, this will always be defined. It's a polynomial, and there are no sudden endpoints. This domain is just all real numbers, so it's not cut off with a closed interval. So we need to find where's this 0. The critical numbers. That'll be when x plus 8 is 0, or in other words, x is negative 8, or when this piece is 0, which will be at negative 8/3 if you just do the algebra there. So you set this part equal to 0, you get x is negative 8/3. So these are the critical numbers that we need to classify. These are the candidates for local maximums or local minimums. So let's put a square around those. They're important. Remember, the second derivative test only applies to this type of critical point anyway, where the derivative is 0. And that's what we're dealing with here in this problem. So those are the 2 points to test, where x is negative 8 or negative 8/3, because that's when the derivative is 0. To use the second derivative test, we plug them in to the second derivative. So here, this is f double prime of x. So this was our first critical number, negative 8. Plug this into the second derivative, and we determine, is it positive or negative? Oh, that's my cat. Negative 24 plus 16. That is negative. So that means that we're concave down. So the graph looks like this around this point. That means we're dealing with a maximum. So we have a local maximum when x is negative 8. This time I'm just giving the location and not the full point. I'm not giving the y value. And we check the other one. It's not a guarantee that it'll be a local minimum. We have to check for certain. So we plug this into the second derivative, which we see up here at the top. Notice these 3's will cancel. So I have a negative 8 plus 16 in there. This will ultimately be positive. So that means my graph is concave up around here. So we're dealing with a minimum. Local min. Again, we'll just give the location without the y value. So again, I prefer the second derivative test most of the time over the first. You just have to be careful because it doesn't apply to every situation, only the most common type. All right, next time we will talk about absolute extrema. So not just maximums and minimums in their little neighborhood, but overall for the function.